Okay, I have started recording. Okay, let's begin again. So for those who are catching up later. All right, so as I was saying just now, chapter 6, we are going to talk more about combinational logic circuit. So what is combinational logic circuit? So a combination logic circuit is nothing but a set of logic gates for a special function. So they're put together in some fancy way, they're connected together in some fancy way to perform a specific function. For example, like we can put together a few logic gates to perform addition. We can put together a few logic gates so that they can perform subtraction and so forth, so on and so forth. Okay, so these are a few of the combinational circuit that we will cover in the class. Okay, I am not going to cover all of them because I believe that the real learning only happens when you discover them. So I am going to teach you a few of them, and I'm going to teach you how to learn the remaining ones. Okay, right. So in today's class, we are going to cover this one, binary adders and subtractors. And in future class, we'll cover a few of this, and the rest, I leave it as a homework to you guys. All right, so let's talk about this binary adder. So binary adder, as the name suggests, it's a very simple circuit. It does nothing but adding. Okay, the name also gives you the answer already. Right, so it performs the most basic arithmetic, that is addition. Okay, addition, and the numbers are added in parallel. Okay, we'll talk about. I'll show you guys what does it mean by that. And this also uses the 2's complement number system. Okay, so you can think about this binary adder as you have your calculator, right? So in your calculator, you can imagine that there's one block inside there that can do addition. Okay, there's one block. What I mean by block is a set of logic circuit, that is able to do addition. So that is a binary adder. So why is it binary adder? Why is it not decimal adder? Okay, again, in computers, computers work best with binary numbers. So if you want to add something else like a decimal or something, what it's going to do is that you key in your calculator, yes, in decimal, but internally, behind the scenes, what it's going to do is it's going to convert this into a binary. Okay, so that is why we are talking about binary adder, not decimal adder or octal or any other kinds of adder, because this is like the most fundamental adder. Okay, so let's talk about in more detail. So in binary adder, you have two types of binary adder. So one is called the half adder, and the other is called the full adder. They work the same way, but with a slight difference. Let's take a look at how they are different. So this is what we call a half adder. So if I were to draw this as a block diagram, so let's imagine that inside here, there is a block diagram here, and this is a half adder. So what this half adder doing, it does is that it takes two numbers, okay, two numbers as an input. Let's call them A and B. Okay, those are the operands, okay, operand A and operand B. And what it does inside here is that it's going to add everything up and spits out the answer. So the answer will be the sum and the carry out. So that is as simple as it gets, right? So you give it two numbers. These numbers must be, yes, it must be 0 or 1. Okay, and do this, 0 or 1, and then it's going to pick whatever you give it and it's going to add together. For example, you give it a number 0 and 0, it's going to do the addition. Okay, 0 or 1. Okay, like that. Right, so it gives you two numbers. One is called the sum, the other one is called the carry out. So over here, what I'm doing is that I add together 0 plus 1. So this guy over here is the sum. So what about the carry out? So because there is no carry out, so the carry out over here is 0. Okay, so this is the carry out, or sometimes we write it in short form as C0 or CO. Okay, carry out. Over here is also a carry out. Carry out, and this one is the sum. Of course, you can also give it like this. Like if you pick two numbers and they are both ones, and now you have a carry out of 1 and you have a sum of 0. Okay, so that is in short how this half adder works. And you can imagine that inside this half adder, you have like a few logic gates away, maybe AND gate and maybe an OR gate, maybe an XOR gate connected together, and then connected together in some ways that will give you the answer. Okay, so we'll look at how is it connected. Like after this, we'll start deriving how is this half adder constructed, okay, by using K-map and so forth. So short story, that's the half adder. What it does, it takes you two numbers A and B, and then it gives you the answer by adding it into a sum and carry out. Okay, half adder. Simple, right? All right, let's take a look at the next one. All right, so half adder truth table. So this is the truth table for half adder. So A and B is the operand, and S and C out, those are the output. So we can complete this this truth table rather quickly. So let's just do that. So over here is 0 plus 0. So the sum is 0, and the carry out is also 0. And over here we have 0 plus 1, and in this case the sum is 1, carry out is 0. And over here we have the sum is 1, carry out 0 again. And over here 1, 1, and you add them together, the sum is 0, and the carry out is 1. Okay, so this is the truth table for half adder. Right, let's take a look at the logic circuit. So now you have a truth table like this. Can you come up with a logic circuit from a truth table? Does it sound very familiar? Like in your in all of our assignments, right? You were given a truth table, and then next you were told that, okay, now give me the logic circuit from the truth table. So can we do the same for this? Yes, we can. Okay, so you have a truth table, very simple one truth table. And how do you get truth table from? How do you get logic circuit from truth table? Remember, we have a tool that we use. I suppose right now that tool will be very familiar with you guys already.
K-map?
Yes, exactly. Right. Thank you for those who answer. I don't feel as lonely if you answer. All right, so let's try this. We have this truth table, and by using K-map, now we can get the truth table out. So let's try that out. So we have like this, A, we have B. Okay, this is like a very simple map because it only has these two variables, 0, 1, 0, 1. Okay, so let's try this. Okay, so how many K-maps do we need? 1. Because like we have K-map only caters for one output, right? So we have 0, 1, 1, 0. So we have 0, 1, and then 1, 0. Now, what about this? Okay, so the answer is for this, you need a K-map as well. So we have a K-map for sum. So this is how we do it. For sum, and then this is for C out. C out, we also have this A, B, yeah, so 0, 1, 0, 1. So let's do that. Okay, so it's like 0, 0, 0, 1. So we're going to map it here, 0, 0, 0, 1. Okay, now we have the K-map. Now, what's the next thing to do is to group them together. And once we get the group, and voila, just like that, we get the circuit. Let's try that. So let's just change this to other colors so that it's visible. Right, so let's take a look at this K-map over here for sum. We see that, is there any possible group over here? Can we group it like that diagonally? No, there is no adjacent ones. So it looks to me that the only way to group this is like so. Okay, so let's get this one out. This one is A, B bar. And what about this? This one would be A bar, B. Right, so that's the only way for you to group. I don't see any other way. So I'm going to write here S is equals to A bar B plus with A B bar. That's the equation for S. Okay, that's what we want. And from this equation, you can already draw the logic gate, right? So there's like an OR gate here, there's an AND gate, and there's a NOT gate over here. Okay, so that is one done. What about the other one? So for this one, there's only one lonely one over there. Right, maybe it's lost. Right, so the only equation that we can get for this is C out is equals to A, B. Is that A, B? A and B. Okay, so this is our equation for C out or carry out. So then, what is the how does the circuit looks like? Okay, so the circuit would be a combination of these two things. So what we can do is that let's just draw a C out over here, and let's just draw a sum over here. So this, you can imagine that to be the output, and carry out is just A multiplied with B. So that is just AND gate. So this is an AND gate over here. Okay, and you can put in like A over here, B over here. Okay, so this one goes here, and this one B goes into this. Right, so that is C out. What about sum? Sum is like what? A bar, B, and then you have A, B bar. So you have some kind of AND gate, like two AND gates, and you have a OR gate like that, and then this two AND gate goes into this OR gate. So the first one is let's just take it here, A bar and B. So we have over here A, so we are going to put this A, draw it like this, and then we're going to go to a NOT gate that gives A bar, and also now it's going to take here, and B goes into the first AND gate. The second one is A, B bar. Second one is over here. We have okay, A, it's not overlapping over here, and you have B bar. Okay, there's so many ways you can draw this. So try to draw it as less messy as possible. Okay, so that will be this second term over here. Okay, and just like that, what we have over here is a half adder. Okay, so remember this. Remember this. So it turns out that inside of this block is this circuit over here. Okay, that is how we get a. That's how we derive the circuit of a half adder, right? So if you want, you can draw a like a box over here, inside here. So inside here, this is like this is your combinational circuit, and its name is half adder. Okay, what it does addition. Okay, it does simple addition with A and B, and then it gives you carry out and S. All right, so that's how we get the circuit for half adder. Easy, right? So easy. However, I want to highlight one more thing over here. Do you guys notice what is wrong with this and what is like not wrong? It's like what is, looks like something is missing for this equation. Do you guys remember what is this equation? Can this be simpler? Okay, so this, it turns out, is the equation for XOR gate.
XOR?
Okay. Yes, sorry, someone said anything?
For the XOR gate?
Yes, exactly. This is an equation for XOR gate. So rather than using basic logic gates like this, we can also write it in XOR gate. So this would be A XOR B, like that. Okay, so if you want to use XOR gate instead of this AND gate, NOT gate, and OR gate, then your circuit will be much simpler. As simple as this. Okay, so this is A XOR with B, and then this one will be A B. Okay, remember, this is what we have inside this block, half adder. Okay, half adder, block diagram. Okay, so now you guys have discovered how you actually derive the circuit for half adder. Now we're going to do the same for a full adder. So take a look at this one. So we're done with half adder. Half adder is just two numbers A and B, you add them together, it gives you the sum and gives you the carry. That's simple. Now let's take a look at full adder. So full adder is very, very similar, except that in full adder you have this one more input, and that input is known as the carry in. So if you were to put it into this mathematical form over here, it looks like this. You have A and B, and you have one additional one called carry in. So what it does is the same. It's going to take all these three things, it's going to add them all together, and it's going to give you sum and carry out. The difference is only you got this over here. Okay. Now let's try to do the same thing. Let's try to derive the circuit. So what we want to know is what is inside here, what is contained inside here for the full adder circuit. All right, so this is the full adder truth table. So the truth table has A, B, and C as the input, and as you have known. So let's just quickly fill this truth table out. It's just going to do the addition of all the terms A, B, and C. Right, so we have A, B, and C. It's going to add them all together, sum 0. So 0, it's going to add this one together, 0, 0, 1. The sum is 1. There's no carry. It's going to add this one together, 1, and then like 0, 0, 1, 1. Now you have 0, and then you have this carry. So 1, 0, 0, your sum is 1, and then you don't have a carry. So 1 plus 0 plus 1, 1 plus 0 plus 1 is 0. It's 1. 1 plus 1 plus 0. Again, you have this one, 0, 1 over here, 1, 1, 1, and finally you have this like that. Okay, let's do a quick check. Okay, looks right to me. Okay, now we have the truth table for S and we have the truth table for C out. Now let's fill in this into our K-map, shall we? So let's just do this for S. Okay, for S. So we have over here A, and let's just do B and C. Okay, I'm just gonna write C again because I think like C in is like very okay. It's the same thing. I'm just gonna make it short over here by writing just C. Right, A, B, and C. Let's just fill in the map 0, 1, 1, 0. So you have like 0, 1, 1, 0 like that. And you have 1, 0, 0, 1. So you have 1, 0, 0, 1. Okay, looks easy. Now let's get the equation for S. So the equation for S is, okay, what's the group like? So, looks to me like we have a very strange situation over here, just like before. What is it? That is, we don't have any ones that are like side by side, that are adjacent to one another, like vertically adjacent and horizontally adjacent. We don't have that. We have like this, like this, but you cannot group it like this in this direction, right? All you can do is like vertical or horizontal grouping. So let's try to group it as best as we can. Over here, it looks like it's a lonely one. It's another lonely one over here, and that is the same. Okay, so what is going on? We will have four terms. So this first term would be A. Okay, I'm writing for this one, right? Writing for this one. A, and that would be B bar, C bar. Okay, that's the first one. Then down. First one down. Now let's write for this one. This one would be A bar. Then it's also B bar and C. Okay, this one. Third one is A. It's A, and then it's B, C. And then it's the last one is this one. Let's do this. Is A bar like that, B and C bar. Okay, so this is like our equation over here. But it doesn't look very simplified, right? Do you agree with me? Right? It looks like there are some things that we can simplify, but we cannot actually simplify this using K-map. Okay, so it turns out that this pattern is a very famous pattern. Okay, so this pattern, what pattern is this? So this diagonal pattern, like this one, and then here, and then you have one here, and then you cannot group them together. So this pattern is known as a checkerboard pattern. Checkerboard. Okay, like like you play checkers, chess. Okay, so this is known as a checkerboard pattern. So this is the term that they use. So if you encounter this checkerboard pattern in your online browsing or online learning, or even in YouTube, like they will simply say, oh, there's a checkerboard pattern, and every time you have a checkerboard pattern, you can simplify it to easy. If you have a checkerboard pattern, you can simplify it to this. Okay, so anytime you see a checkerboard pattern, you can simplify it to the 3 inputs XOR it together. Okay, 3 inputs, you XOR them together. In fact, just now, you also saw that we had a checkerboard pattern. Let's go back to the half-added one, right? Right, so remember this? We also had this checkerboard pattern over here. See, this is also a checkerboard pattern. And as a result, the checkerboard pattern can be simplified to just the 2 inputs XOR together. XOR the input together, okay? Which is also what we get from this, right? Remember? So checkerboard pattern is like a shortcut. You see checkerboard pattern, you just take the inputs. You have 3 inputs, you XOR them. You have 2 inputs, you can also XOR them together. Let's go back to our full adder over here. So we have this checkerboard pattern over here, and right. So, and to simplify this, you can just simplify to A XOR B XOR C. Okay, but what if you want some kind of a proof? Okay, I cannot just say that, oh, if your checkerboard pattern, like, and then you can just simplify to this. So, is there any proof that this long equation here is actually equals to this? Okay, now I'm going to show to you how does it become like this? Okay, A XOR B XOR C. So let's take a look over here. We are going to try to simplify this using Boolean algebra laws. Okay, this checkerboard pattern cannot be simplified with K-map, but it can be simplified with Boolean algebra laws. Okay, take a moment and let's see. So we have S over here, and now we are seeing that there are some common terms that we can factor out. Don't you notice that? Okay, so what are the common factors? Okay, if you take a look here, this term and this term, is there anything common that you can factor? Yes, right, it's A. And what about this one? This term and this one term. Is there any common factor? Yes, A bar is common. So let's just take out this common factor and see what we get. Okay, let's do this one first, A and this one. So we are going to put A here, and we are going to have this. Okay, and we are going to put in, A, and then we have B, C. Okay, cool. So that is the common factor out. What about the second one? Over here, we are going to factor out this A bar, and then we have B bar C, plus everything here is B, C bar. Okay. All right, so let's see what is next. So do you notice what I'm seeing over here? Okay, B, C, B bar, C, B, C bar. Isn't this the same as the previous one we saw? Isn't this the same as this? You see, A bar B is actually A bar B plus A B bar. They are. It's actually this, right? So that's what we have over here. That is also what we have over here. Okay, so that's also what we have over here. So this one, actually, you can rewrite this with like so. Okay, and over here, what is this? If you recall, this is the XNOR pattern. Okay, so this one is exclusive NOR. Okay, so this one inside the bracket, it is an equation for XOR, exclusive OR. Now over here, this one is the equation for exclusive NOR. Okay, exclusive NOR. One is exclusive OR, the other one is exclusive NOR. Exclusive OR and exclusive NOR. Okay, sorry. Okay, so now I want you to imagine. Let's simplify things a little bit more, right? Let's now I'm going to change this in color again. Okay, let's imagine that everything inside here we are going to simplify. Instead of writing B, X, or C, I'm just going to write this as X here. Okay, instead of B, X, or C, I'm just going to write as X over here. So imagine that. Okay, that is going to make our equation looks like this: A, X bar, like that. Okay, because there's a bar on top. A, X, A bar, X. So are you seeing what I am seeing over here? This is, again, the pattern of exclusive OR, right? So this is a pattern of exclusive OR. So I can rewrite this like this: A, XOR, X. And remember what is X? X was this. And I can replace this X with that. So it would be XOR C. Okay. So this is the proof that this checkerboard pattern actually is this. This is how we get this. Okay. So there is some like work over here to prove it. But as a shortcut, when you see checkerboard pattern, you immediately know that checkerboard pattern is actually just the XOR of all the inputs: A, XOR B, XOR C. Okay, just like what we have shown, what we've seen over here on this board, on this slide over here. Okay, so far so good. Any question on this checkerboard pattern? All right, so if there's no question, let's proceed. Right, so once we know this, okay, actually we're not done yet. So what we have done is just this one, S. Okay, so the logic circuit for S is this. Okay, so can we do the same for C out? Yes, we can do the same for C out. You can just map this one into another K map. And shall we do this? Okay, let's do this now. So 0, 0, 0, 0, 1. So you have 0, 0, 0, 1 like this, and 0, 1, 1, 1. So you have 0, 1, 1, 1. Okay, so let's try to get the equation over here. This is one group, this is one group, and this is one group. Okay, is there any other way you can group it? I think no. Okay, so there's three equations over here. So the equations are carry out is this first group over here gives us A, C. Okay, the second group over here gives us A, okay, A, B. And this third group over here gives us B, C. Okay, so there you go. This is the equation for C. Okay, now we have the equation for S and the equation for C. Then we can draw this out, and it looks like this. So we have XOR. You have XOR, gives you the sum, and you have some AND gate and gives you the carry out. So this is what the content of a full adder look like. Okay, so if you imagine this is a full adder block diagram. Okay, in this block diagram, inside it is these logic gates. Okay, so these are the full adder. Okay, full adder. So it's got like 3 inputs and it gives you 2 outputs. Yeah. All right, so that is how you derive the full adder. So we've done half adder and we've done full adder, and I've shown you guys how do you derive them from the truth table itself. And it turns out that you can use the same technique to derive the circuit for any other combinational logic. Okay, right, same technique. Once again, it's truth table, K-map. From K-map, you get the logic gates. Right. So let's take a look at what are some other ways that we can make use of these binary adders. So we're going to talk about parallel adders over here. So just now we looked at full adders, right? So this full adder can only do A plus B plus C. So which means that all it can do in a full adder. So let's go back to our slide, our previous slide, right? So in a full adder, right? In a full adder like this, so you can do A plus B plus C, right? A plus B plus C. So A can be 0 or 1, B can be 0 or 1, C can also be 0 or 1. So the best you can do, the largest number that you can do is what? 1 plus 1 plus 1. That is the largest operation that you can do, right? So 1 plus 1 plus 1, it gives you this as the answer. But you know, in the real world, there are bigger numbers than this 1. Okay, what if you want to do like 1 1 plus 1 1 plus 1 1, right? What if you want to do this? How? We could not do this with this one single full adder alone, but we can make it a parallel adder. So that is what I'm trying to show you guys in the next slide over here, which is parallel binary adders. So parallel binary adders, it means that you can take any adder, full adder, half adder, and you can combine them so that they can perform a larger operation. So this is how you combine them. Okay, this is how you combine them. So over here we have full adder number 1, and over here we have full adder number 2. Okay, so take a look at this full adder. So it's got A1, B1, and then it's got this carry in. So this carry in, and then it will give you two numbers as the output, sum 1, and then it gives you the carry out also. And that in terms becomes the carry in for the next full adder over here. Okay, so that is how we combine it. So if you look at the addition, this is what happens. Like you have A1, and you add them together with B1. So this is what happens over here, right? So you give it two numbers over here, it does the addition, and it gives you the sum 1, which is this guy over here. And it also gives you the carry. That carry needs to go to the next adder. So over here, if there is a carry, this carry needs to go to the next adder, right? So that is why the carry out over here is connected to the next adder as a carry input. So over here you have this operation A2 plus B2 plus with whatever that comes in over here as a carry. Okay, and it gives you the output as sum number 2, and it gives you the carry out number 3. Okay, or you can write it as sum number 3 also. Okay, right. So one thing that you might notice is that if you're doing lab, okay, you want to make this be connected to the ground. Because why? Because you see over here in the first column over here, is there any carry input in? Okay, so there's no carry input in. So but in a full adder, you have this carry input in over here. So if you do not connect this to the ground, ground represents 0, okay, 0. If you don't connect this to ground, sometimes this value can be 1, okay. So what I'm trying to say over here is that if you don't connect it to the ground, the value that comes in over here is an uncertain value. It can be 0, it can be 1, it depends on the, it's like a random value coming in. So you don't want this random value to come in, because like if this random value happens to be 1, and it's going to mess up your addition, right? So that is why if you're doing lab, now you want to connect the carry in of the first full adder to ground, so that you get, every time you get a 0 over here, okay? And this will make sure your results are correct. So that is how we combine full adder. You combine multiple full adder forming a parallel full adder. Okay. Right. So we can also extend this to multiple full adders. So for example, we can make a 4-bit binary adder. Okay. So for example, what we're doing here is that we construct 4-bit binary adder using full adder circuit. Draw the block diagram. Okay. So the inputs are 4-bit binary number, and the 4-bit binary adder are 4-bit number. Okay, so long story short, we have 4-bit number A3, A2, A1, A0, and we have another 4-bit number B3, B2, B1, B0. Now we want to add them up together, and and this one you would get your answer as sum1, sum2, sum3, and sum4. Okay, and there's a carry out also. This is the operation that we want to perform. So how do we make our adder? How do we connect our full adder together to make sure we can do this? So it's the same. It's the same like the previous one. So we have over here full adder 0, full adder 1, and then you have a full adder 2, and then we have full adder 3. Same thing. So the first one we connected to ground. Okay, because this is the first one, and then this first adder is going to do the addition between this, and then the output, the carry out will be connected to the second adder. Then the same thing, this carry out will be connected to the next adder and the next adder. Okay, so this is how we make our adder perform a 4-bit addition. Okay, all right. So this is also known as if you're looking up online, you would see that this is also called a ripple adder. Okay, ripple adder. So why is it ripple? Because the output of first adder ripples to the other one, and then it ripples to the other one like a wave. Okay, so that's why it's called a ripple adder. That's just a side note. So we can. Turns out that what if we don't want 4-bit? What if we want 8-bit? What if we want 16-bit? What if we want more than that? So we can always reuse this in the same way. So over here we have a 4-bit adder. 4-bit adder. Over here we have 4-bit adder. So we can cascade this 4-bit adder together like that. Okay. Take a look at the carry out. Goes into the carry in of another 4-bit adder. And now we form an 8-bit adder. So which means these two adder can add 8-bit numbers. Okay, so you can do this addition like this now. 0, 0, 0, 0. Example, you can do this operation now. Okay, so because these are 8-bit numbers, right? Previously 4-bit number, you can only do this part of the operation, but now you can do more. Okay, so what if you want more? Yeah, you can cascade them together like this. You can form a 16-bit adder. Okay, so what I'm trying to show you guys over here today is that this combinational circuit is very beneficial. Why? Because can you imagine you want to construct the K-map of this 16-bit adder? It's going to be like crazy. There's so many things you got to do to construct the circuit of this K-map of this large giant circuit. But instead of doing that, what we can do is we construct the K-map of the smallest element, that is the full adder, and then we use that and combine them together to form a larger circuit. So that is how combination circuits can be very useful. You can think of it like a Lego block. Okay, so you have one Lego block and you can stack with another Lego on top of another Lego block to form a larger block. So this is what that's going on over here. So what we have to do is construct the K-map for just one full adder, and then we can reuse that by cascading them together, by connecting them together like this, and to perform a larger adder. Okay, so that's why it's known as the combinational circuit, because you can combine them in various ways to perform larger function. Okay, so that is adder. All right, so I'm going to talk a little bit about this propagation delay. If you remember from the last class, there is a problem if you connect things in this way. Okay, remember about propagation delay. So in propagation delay, it means that this full adder is going to take some time to perform the adding and then computing the output, and then it's going to send this output over here. Now, in the meantime, the output over here, they are uncertain. Okay, they are uncertain. So there is a propagation delay, and then the output over here is going to wait for the previous output, and then it's going to get it. It's going to wait, and the last adder is going to wait the longest. So during that waiting time, there can be a glitch. Okay, there can be a static 0 or a static 1 hazard in between. So there is a problem of propagation delay if we cascade too many adders like this. And the solution is this. The solution to this problem is something we call these are the two solutions possible. One is to use faster gates. We need to say we use a gate that has a very, very small delay so that the last adder doesn't have to wait for too long. until it gets the output, and that would reduce the chances of getting a error or getting a hazard. The other solution would be this one. It's called carry look ahead adder, or CLA. So I'm not going to talk about this in this class. What I want you to do is to check out these two videos. Okay, to check out these two videos and see what this carry look ahead adder is like and what it solves. Okay, it's supposed to solve this propagation delay problem. Okay, this one is maybe your homework today, and in the next class maybe we'll have like a simple quiz or something on carry look ahead. Okay, so do take note on that. Okay, so we talk about adder, we talk about full adder, we talk about half adder, and we also talk about how we can combine those adders into a form, into a parallel form that can support more digits, that can support the addition of more numbers, right? And what about subtraction? So subtraction is the same. So we can also perform, we can also have a circuit for a subtractor. Okay, circuit for a subtractor, nothing different, except the operation is different, of course. The process is the same. How do you derive a circuit for a subtractor? First, start with the truth table over here. So we have truth table X and Y. So B stands for borrow and D stands for difference. Okay, so difference is the result of your subtraction, and borrow if you have any borrow. Okay, for example, you're over here, you have 0 minus 0, the difference is 0. So you have 0 minus 1. Okay, so the result would be you have a borrow and then you have a answer of 1. Okay, remember this, 0 minus 1. So you can borrow it somewhere, then you borrow from somewhere, and then you get 1. Okay, so that's how you get this 2. Difference is 1 and you have a borrow. Right, so these are the truth table, and if you make this truth table into a put this truth table into a K-map, this is what you get. The equation is D and B, and you have this logic gate as your you have this as your logic circuit from the equation, right? That's a subtractor. So we have also half subtractor. This is known as half subtractor, and we also have a full subtractor. Okay, so this is the concept is very similar to, sorry, why is it jumping around? We have half subtractor, and half subtractor only deals with 2 inputs, and we also have a full subtractor. Full subtractor deals with 3 inputs. Okay, so instead of carry in, you have a borrow in. Okay, borrow in, and what happens over here is that you have 3 inputs that you need to subtract altogether. And if you put this into a truth table, it will look like this. And how do I get this? 2 equations from K-map. Okay, I don't want to bore everybody by doing K-map again and again. So I believe you guys are familiar already because we've done so many K-map, and it's also very similar to the K-map we did in the full adder. So do try this out and make sure you get this as the equation. Okay, so you have D and then you have B out. Okay, BOUT over here stands for borrow out. All right, so the next question is, okay, so I have an adder, I have a subtractor, but what if I don't want to make this subtractor circuit by doing the K-map? The question is, can we use the adder, binary adder, and can we make it do subtraction? That is the question. Can we take the adder circuit and can we make it do subtraction? Right? The answer is yes. So how do we make an adder circuit do subtraction? Okay, remember this. So if you want to do A minus B, remember, if you want to do A minus B, you can do A plus 2's complement of B. Okay, so A minus B, we can also write it as A plus with the negative of B. Okay, so how do you get the negative of B? It's easy. You take B and then you make it into the 2's complement form. Okay, that is how you make adder circuit do subtraction. Okay, so you're still performing addition over here because A plus with the 2's complement of B. That is our target over here, right? So we can still use the adder circuit over here. Okay, So how do you get 2's complement? Remember, to get 2's complement, first step is you invert the b, and second step is you add 1. Invert and add 1. That's all you need to do to perform to make this into a 2's complement number, and then you add them with 8. Right. So now let's take a look at how we can do how we can modify this circuit into a binary adder slash subtractor. So this is what I'm trying to do over here. So we want to have a circuit that can perform both functions. So we have an adder circuit and a subtractor circuit. Okay, it does both operations. And how do you determine that operation is by using a selector. So if you're doing like lab, you might have come across this lab module that that asks you to construct a circuit that can perform adding and also can perform subtracting at the same time. So how do you do that? So it turns out that we can use adder circuit to make this circuit. Okay, this will be my last slide today. So pay close attention because this will really help you understand what you're doing in the lab. Okay, so let's go to this empty slide, and I'm going to start showing you guys how we do this. Okay, so we have full adder circuit here. So let's suppose our subtractor and binary adder subtractor, we want to perform it with a 4-bit numbers. Okay, you can do 8 bits, 16 bits, but it's the same thing. Okay, so to not complicate the circuit, let's just limit our case to a 4-bit number. Okay, so we want to do 4-bit addition, and we also want to do a 4-bit subtraction with this circuit. Okay, it can have it has this both two functions in one circuit, and it has a selector to select which function that you want to perform. So we are going to use the full adder circuit. So we have the full adder over here. So this is how we are going to do it. Now we are going to do the addition circuit first, right? Full adder, and then they have carry in over here, and this one is full adder. Let's name this full adder 0. Okay, so this one will be sum 0. Okay, let me write this sum 0. Okay, and this one is the carry 0, and I am going to put this carry 0 into the next one. Okay, it goes into the input of carry in of the next adder. This is carry in, this is full adder 1. Then produce sum 1, and then the same thing over here, going to ripple into the next adder. Oh, this better. Full adder 2. Then this produces sum 2. Then this output goes to plus full adder. Full adder. Okay, forgive my poor drawing. Okay, so hopefully you're seeing this pattern over here, sum 3, right? Okay, so remember to label the inputs. So you have A0, B0 over here, and of course you have A1 and you have B1 over here. B1, you have A2, B2 over here, and you have A3 and B3 over here. Okay, so this one will be carry out. Okay, or yeah, you can write this as carry out, or you can write this as sum 4. Okay, because it doesn't go anywhere. So the operation that we are trying to perform over here is as follows. You have A3, A2, A1, A0, and then you're going to add it with B3, B2, B1, and B0. So the answer would give you sum 0, sum 1, 2, sum 3, and you can write it here as sum 4 as well. Okay, so this is what we are trying to achieve over here with this circuit. Okay, now Do you see any problem? This circuit does what? It does addition with no problem, right? It does addition with no problem. Okay, so what if now we want to do subtraction? What if now we want to do subtraction? So instead of adding, we want to do subtraction over here. So what happens if we want to do subtraction, but we're not going to change this circuit? Okay, we're not going to change this circuit. So the circuit is still a full adder, but we perform the subtraction operation. So as I've said in the last slide just now, so if you want to do A minus B like that, so but you want to use adder, as the circuit. So what you can do is this instead. Use the adder circuit, but now you make this be a complement. Okay, you can make this be a complement. So how do we make it into a complement? We can invert it and we can add 1. Invert and add 1. Okay, so of course, like how to invert and how to add 1 is very simple. So you can put a NOT gate over here, no problem with that. You can put a NOT gate over here. That NOT gate will perform the inversion. What about add 1, right? Okay, so here's where it gets interesting. So I can have instead of B over here like this, I can have a XOR gate over here, and I can put in B0 over here. Okay, bear with me. You will see like the magic over here of doing this later. So over here, the other input is I'm going to connect them to a selector input. Okay, selector input. And what happens is that this selector is going to do the inversion. So how is that? How is that so? So remember, for the XOR truth table, so you have you have X, Y, and then let's say F. This is a truth table. Okay. So you have 0, 0, 0, 1, 1, 1, 1, 0. So you have 0. Okay, this is the truth table for XOR. Let's just keep this handy over here. Okay, so now I want this XOR to do inversion. How is XOR going to do inversion? Okay, so let's suppose that this, instead of writing X here, we do B. Okay, B, and then instead of writing Y here, we put in the S over here. Okay, so if I give a value of 0, okay, if I give a value of 0, I want this output to be a 1 over here. If I give a value of 1 over here, I want the output to be a 0. Okay, so sorry, my bad. Okay, if I give a value of 1 over here, I want the output to be 0. 1 0 1 1. I want the output to be 0. Okay, if I give a value of 1 over here, the output I want is a 0. Okay, so what does it mean? What does it mean over here? So which means that if I want my output to be inverted, I can give a value of S to be 1. Take a look at this one. Okay, if my value of S is 1, okay, it will invert whatever value of B that I give it. Okay, take a look at these two rows. Okay, if my value of S is 1, if I give a value of B to be 0, it will give a inverted version of B, which is 1. If I give a value B1 and my S is 1, is my output will be 0. So which means to say that if S is equals to 1, I get inversion. I get the inversion of B. Okay, agree? If my S is equals to 1, I get the inversion of B. If my S is 0, I don't get any inversion, so I get the original number. Okay, if B is 0, it gets 0. If B 1 over here, it gets the value of 1 at the output. Okay, so over here I can already select. If I want the inversion to happen, I give it a value of S equals to 1 over here. If I don't want to happen, I give it a value of 0. Okay, so now that is one part of the equation done. So we want to invert. Okay, we want to invert. and we also want to add 1. So of course, like this one, you can draw the same for B2, B1, and then this one goes to S also. Okay, I can draw Y over here, but it will look messy, so I'll just write S over here. B1, and this is an XOR gate also. This is B2, S, and this is XOR gate, and this is B3, and this is S. Okay, so remember, if I choose S equals to 1, all my B's will be inverted. Okay, if I choose S equals to 1, all my B's will be inverted. If I choose S equals to 0, all my B's will be not inverted. It will just stay the same. So because of this truth table over here, right? Now, what if I want to perform a subtraction? I want to perform a subtraction. The first thing I need to do is to invert the B, and then I need to add 1 to the whole thing. So how do I add 1 over the whole thing? So it's very simple. So you can add 1 through the carry in over here in the beginning. All right. So what if I connect this over to S as well? Okay. So what happens if I put S equals to 1 over here? So if I put S equals to 1 over here, it means that all my B's will be inverted. So it means that I invert all the B's, invert B, and then this S equals to 1 not only goes to invert the B's, but it also goes into this carry in over here. And it also, because it goes to the carry in over here, it gets a value of 1, it adds 1. It adds 1 to your answer. So there you go. We have over here inversion, and we add 1. So what this means? So what this means is that if we put a selector of 1 over here, this circuit will perform subtraction. Okay, so if we want the circuit to perform addition, what happens? We put it to 0. If we put it to 0, all these B's will not be changed. All these B's will not be changed, and it also will not add any value into your answer. It will add 0 as the carry input. Okay, so guys, take a look at this. This is how we make this circuit perform addition and subtraction. But what do we use? We only use a full adder inside here. Okay, we don't use full adder, but we can perform a subtraction. All right, so let me go next. Okay, so this will be the final. Okay, I have like a properly drawn circuit like in the slides. Okay, so after I've exited this PowerPoint, all the scribbles will be gone. So let's just take a look at the drawing. Much nicer drawing. I'm going to erase what I scribble here, but it's the same thing. Okay, it's the same thing. Okay, is there a way to erase everything on the screen? Okay. Is this okay? Okay, so it's the same thing that I've drawn just now. Okay, so over here, what we're seeing is okay, M is the selector. It's just a different name. You can just put M. You can just put S. So if M is equals to 0, it will give a value of 0 over here, and then because the value of 0 goes to every XOR gate over here, it will not alter this. So the result will be addition, and if you change this to 1, then the result will be subtraction. So that is how this adder subtractor circuit works. Okay, so hopefully if you're doing lab, hopefully this is clear to you. There's one extra feature in this circuit is that we have a overflow detector. So over here we have a C4 and C3. So we have an overflow detector. So if C4 and C3, you go into this this XOR gate, if the value is 1, then it will detect as a overflow. So it turns out that let's go back again to this XOR gate truth table. So it turns out that you can write this over here instead of B and S. You can write it as C3 and C4. C3 and C4. Okay, it turns out that if you're doing any operation, if for a 4-bit number like this, if C3 and C4 they are different, it means you have an overflow. Okay, let me illustrate that to you guys, what it means. Okay, so for example, I have 1, 1, 1, 1 over here, and I have so let's say I have 0, 0, 1, 1, 1, right? So these are positive number, you expect a positive number. Okay, so let's just do this addition. So here, and then 1 plus 1 plus 1 is this, and you have this. Okay, so what is C3 and C4? So in this case, we see that this is a positive number. This is a positive number, but the answer is a negative number. So we know from this that there is an overflow, right? We know that there's an overflow. But how do you detect this overflow from the circuit itself? So it turns out that you can check what is C3 and what is C4. Okay, so C3 over here is this guy over here. Okay, so C0, C1, C2, C3. And what is C4? C4 is over here. And in this case, C4 doesn't have value. So C3 is 1, C4 is 0. So in this case, C3 is 1, C4 is 0. So you want it to detect a 1 to indicate that there is a overflow. Okay, so this is the case for there's an overflow. What if there's no overflow? If there is no overflow, C3 and C4 will be the same value. Okay, C3 and C4 will be the same value. Let's try in a case where there's no overflow, right? So 0, 0, 1, 1. I know for sure that this one doesn't have an overflow. Like that. Okay, you have 1 over here. Here 1. Okay, 0. 1 plus 1 is this. 1. Okay. For this one, we know from this workings over here that there is no overflow, right? No overflow. How do I know there's no overflow? Positive number plus a positive number, the answer is a positive number. So I know there's no overflow. But we want the circuit to detect whether or not there is an overflow. So what is the value of C3 in this case? The value of C3 is over here. And the value of C3 is 0. What is the value of C4? C4 is on this column. And the value of C4 over here is also 0. So from this, what we see is that in the case of there is no overflow, the value of C3 and C4 will always be the same. And in the case of there is an overflow, the value of C3 and C4 is different. Okay, so whenever you have C3 and C4 to be a different value, there is 0, then you will have an overflow. Whenever you have a C3 and C4 is the same value, then you have no overflow. Okay, so this is what this circuit over here that's performing. Okay, so that's why over here we have a XOR gate to check whether or not C3 and C4 are the same. So if C3 and C4 are the same, which means C3 and C4 are the same, is row number 1 and row number 4. And we want to say there is a no overflow, or we want to give a value of 0. Okay, if C3 and C4 is the same value. But if C3 and C4 is not the same, now we want to output a value of 1 to indicate that there is an overflow. Okay, so that is how we check if our circuit has an overflow, by using this XOR gate at the C3 and C4. Okay, so this circuit, at the end of the day, this circuit is a very powerful circuit. This circuit is able to, this circuit is now able to do adder. It can do adding if you put a mode to 0. It can be subtractor if you put a mode to 1. And this circuit can also detect an overflow if the value of V over here is 1. And if the value of V is 0, then the results are valid. Okay, so if you're doing lab, you will notice this, that in your adder chip, you have a pin that has an overflow detection. So this is how it works inside there. Okay, so you have a gate over here, an XOR gate over here to detect whether there is an overflow. All right. Okay, so that will be my last slide today. So hopefully this helps you understand deeper on how this full adder works. So today we've covered a lot actually, We've covered from a half adder, we've covered full adder, we've covered subtractor, and we've also come to this slide where we can combine the full adder in this way to make it a adder subtractor circuit. Right? So I hope you guys can understand a little bit more, at least from today's class. So as a homework, what I want you to do, okay, this is what I was talking about in the beginning of the class. So in my class, I really do hope that you guys will not just learn what I teach in the class. You guys will not just learn about logic gates, not just about K-map, not just about Boolean algebra, but there's something much more valuable that I want you guys to learn from this class, and that is the skill of learning to learn. Okay, learning to learn. So why do I say that? So the reason why I say that is that there's only a limited time that I have with you in the class right now. I can only have like 2 hours with you every class. Okay, and that is the limit. In the 2 hours, I can only give you so much in this class, in each class, right? So what I really hope that you can learn is that you learn not only what I teach in the class, but you learn what is out there. You learn, because knowledge is just so wide. There's just there's so many things that is impossible for me to cover everything in the class. So this is the real skill that I want you to learn, and that is learning to learn. Okay, so learning to learn means you learn a way how to learn a new topic. Okay, so if you just learn what I say in the class, that will be like me giving you a fish. So at the end of the day, you get one fish. But I think it would just really be a waste, because there are so many other fish out there that you can get. So what I'm trying to say over here is that instead of you taking the fish that I give to you, why don't you take my fishing rod and learn how you can learn new things? And this is an exercise for everyone. So today we have covered in the class about adder. Okay, and we've covered how do you construct an adder, how do you make this adder work, and how do you combine this adder and turn it into a parallel adder subtractor. Now, there are many other circuits that you can that's out there that you can learn, and I cannot cover every single one. There's just too many of them. So as an exercise in today's class, I want you guys to learn about this one, this circuit. Okay, learn about what is a magnitude comparator. Okay, learn what's magnitude comparator, and things you can find out is this: what it does. These are the basic things that you can find out what it does. How does it work? And I also want you to find out in which application you can use a magnitude comparator. Okay, so these are some of the points, and you can also include other relevant details. All right, and the resource, as I said, the resource is all online resources that you can get. Guys, knowledge is everywhere. All it takes is for you to fish them out. So this is an exercise for you guys to try to fish this knowledge out. Okay, so magnitude comparator. Now you can find out this how it works with these 3 key points, and I'm going to teach you a technique also how to learn anything. So how do you learn anything? Let's say you are totally new to something. My suggestion is this: go onto YouTube, search for this keyword magnitude comparator, and you watch 10 videos on magnitude comparator. Don't worry if you don't understand anything. Just watch 10 videos about magnitude comparator, and by the time you get to the 5th video, I guarantee that you already learned something. Okay, go on YouTube, search for 10 videos about magnitude comparator. You don't have to have a lecture, a 2-hour lecture. Search for those short videos, 5 minutes, 10 minutes video. There are so many of them. Watch all of them, and I bet that you will learn so much more about magnitude comparator in that 10 videos compared to listening to me talk for 2 hours. Okay, and the thing is, you can apply this to any other subject, any other skill that you want to learn. You want to learn how to draw? Watch 10 videos on how to draw. You want to learn how to set up a website? Watch 10 videos on how to set up a website. So that is how you learn how to learn. So these days, this is the technique that I use to keep up with the things that I learn. I'm also learning new things as I go on. One of my recent projects, I'm learning how to set up a website. So that's what that's why this is what I think is very powerful, because no other college, like in your course, there's no way anyone's going to teach you how to set up a website. This is like an electrical course, right? So what if you want to learn how to set up a website? Watch 10 videos on it. What if you want to learn how to cook? Watch 10 videos on it. And I bet by the time you get to the 10 videos, you've already learned so much more compared to those who did not watch the video. All right, so this is something extremely valuable. I really hope that you guys give it a thought on this thing. Learning how to learn is such a very, very useful skill, especially right now, the times where we are learning online. Okay, so that will be my last slide today. And as usual, today also I will release a quiz like after this, and I will release this slide as well. So take your time to answer your quiz. You have 1 day. And if there's any problem, feel free to stay back. And if there's no problem, then I'll see you again on Thursday. This will be the attendance. All right.
Thank you, sir. Thank you, sir.
All right. You're welcome.
Thank you, sir.
Thank you, sir.
All right. You're welcome. If you have any problems, just please reach out to me. Drop me a message. Stay back. Whatever you do, just let me know. Okay. Let me know ahead of time.